Alright, so far we've been talking on derivatives and what they are. Now we're going to talk about some small, like, basic applications and where they can be used and how they can be pretty powerful, right? So, first we'll just start off by the parallels between derivative and the notion of an instantaneous rate of change. Okay. So essentially, what I'm trying to say here is the derivative can be used as a measure of the instantaneous rate of change. Now, what does that mean? Let's break down what rate of change is. So, rate of change. You might have heard of rate of change as being described as the slope, right? It sort of describes how fast are things changing. So if we have a function, right, that's graphed on a y and x value, our rate of change is how fast is y changing with respect to x, right? So if our slope was 2, right, for example, this is just like a normal line, right? So when we know our slope's 2, every time we increase x by 1, our y is increasing by 2. So it essentially just tells us how fast are things changing. And in terms of a function, we often had it defined as f of a plus h minus f of a divided by h, right? And in case this notation seems a bit foreign, if we had a point at a plus h and we had a point a, right? Essentially what we're doing is we're finding the slope between those two lines. And if you remember discussions about secant line, this is exactly what we're doing. We're finding the secant line, the slope of the secant line between 2 points on a given function, right? And hopefully you guys see how to go from this and being asked to find a slope of that to getting to this equation, right? We're just doing y2 minus y1 divided by x2 minus x1. And so y2 is f of a plus h, right? This is some function f. And then y1 is f of a, and then x2 is a plus h, but when we subtract it from a, we're just going to get left with a, right? So what is instantaneous, though? Instantaneous rate of change. So when you think of an instant, what it's basically saying is this is over the rate of change over some non-zero time period h, right? But often when we're doing rate of changes over a pretty large interval, we're averaging things out. Like imagine if we had a function like this, right? And this equation, the top one, the rate of change, is like the secant line through that equation. And we can kind of understand how using the rate of change equation is not going to tell us the full picture of how things are changing at a certain point. And that's where the whole notion of instantaneous rate of change comes in, right? Rate of change can be useful over if you want to find out how things are changing over an interval. But what if we want to know how things are changing at a specific point, right at that instant? That's when we need the whole notion of an instantaneous rate of change. And what would that mean, right? If we had our instantaneous rate of change, that means we sort of want we sort of want to sample an interval that's extremely small. And that means that we want a plus h and a to be very close to each other, and our difference in x to also be very close to each other. And that's where we take our notion of limits, and we add the limit as h tends to 0, which basically means that we're sampling the rate of change at an interval that's basically getting towards 0. And we know that this whole idea of sampling, getting towards that sample of our interval being 0, is the whole idea of the derivative, right? The tangent line, the slope of the tangent line at that point, right? And we know that this is the definition of the derivative of a function at point A, right? So we can sort of see how there's a parallel between the derivative and the notion of an instantaneous rate of change. In fact, the derivative at at a certain point describes the slope of the tangent line at a point, and that is the instantaneous rate of change at that point. And that's the whole idea of this applications of derivative. Anytime we want to find, so any time we want to know the rate of change at a specific point, we know to use derivatives. Our answer lies in finding the derivative of the function, right? Evaluating the derivative at the derivative function at the point we care about, and that's gonna tell us the slope of the tangent line. And the slope of the tangent line, right? That's just the rate of change at that specific point, and that is our instantaneous rate of change. So now this seems a bit abstract, right? So let's try to hammer in these ideas through certain examples. So this example 1 is about circles. Okay. So part A, find the rate of change of the area A of a circle with respect to its radius r. Okay. So essentially what this is saying is we have the area of a circle, right? We know that that is pi r squared, right? We want to find out the rate of change of that area with respect to a certain r, right? And so essentially what it's saying is how much does the area, when we find the rate of change of the area, we're saying is how much does the area increase or decrease if we have an r at a certain point, right? So let's find the derivative, right? So derivative of a, so a prime is equal to 2 pi r, right? And that's basically our instantaneous rate of change of the function, of the area function, right? So for example, this goes on to part B, evaluate this function. So evaluate for r equals 5 and r equals 10, right? So if we were to do r equals 5, so we'd get 10 pi, and then r equals 10 is 2 pi times 10, which is equal to 20 pi. We clearly see as we're increasing our radius, the rate of change, so the amount our area is changing by, does get larger, right? Which makes sense because we have an r squared term, so whenever we're increasing our radius, the amount our area is increasing by keeps increasing as well. Right, so essentially, by finding the rate of change formula, we have sort of internalized the whole notion of like, before we wouldn't know exactly by how much our area is increasing, but now we know that at 0.5, the instant at 0.5, our area is changing by 10 pi. Before, we wouldn't have that whole notion of like, what is our instant change? All we knew is that as we increase our area is changing by a larger and larger factor. But now with the whole idea of instantaneous rate of change, we know by how much exactly is our area changing. Okay? So now let's go on to another application. Motion. So the second application is motion, right? So if anyone's ever taken a physics class, we have the notion of displacement, velocity, and acceleration. There's also jerk, but I mean most physics classes don't really need to cover jerk, right? So displacement is the whole idea of how far away are you from your starting point. So if this was your starting point, right, x, and if you're at x plus h, our displacement is h, right? And then if you're at x minus h, our displacement would be minus h. Let's say you were at x and you traveled to x plus h, and then you came back to x minus h, and then you went to x, right? What would our displacement be? Right? You might be tempted to do h plus h plus h because we traveled h, right? And then to come back, we traveled 2h, and then to come back to go to x again from that, we travel another h, and that would evaluate to 4h. But that is the distance we covered. Distance and displacement are defined differently. Again, displacement is how far away are we from our starting point. And so if we return back to x from no matter like what we traveled, our displacement would be 0. All right? And similarly, like if we traveled, across the world and then ended up at like x plus 1, right? Our displacement would be 1. But our distance might be the length of the world and then plus that little 1. And velocity, right? So velocity is, so now we go to velocity. So velocity is defined. So first, before defining velocity, I'll define average velocity. Which is essentially defined as the change in displacement over the change in time. And then, so this is displacement. And then the delta is change in. So this is change in. Okay. So that's what velocity is defined as. And if we were to sort of get into notation that might come in handy later, we can do something like this. So that's f of t plus delta t minus f of t divided by delta t, right? So this is, we are anchoring at point t, and then this is some delta, and then we're dividing by our total difference in the time, which is delta t. And that's our average velocity, right? So notice how this is the average rate of change. We can kind of see this as velocity being the average rate of, like the way average velocity is defined is average rate of change of displacement. Right? We can kind of get that notion from just how physics works. Now, what if we want to find out our velocity at an exact point, right? And hopefully you guys can see what I'm trying to imply here, right? Let me just move to a new page. So from previously, we had defined average velocity as delta s over delta t, which is equal to f of t plus delta t minus f of t divided by delta t, right? And this is the notion of average rate of change of displacement, right? And we get this directly from our discussion of just rate of changes and how we can interpret this sort of looking equation right here, right? And that average rate of change of displacement is defined as average velocity. Right. But again, I sort of alluded to the problems of having the notion of average. We sometimes, actually pretty often, we want to know how things are changing at an instant, right? So what if we want to find the velocity at an instant? We would have to make delta go to 0, delta t go to 0, right? And that essentially means we have to find the limit as delta t goes to 0 of f of t plus delta t minus f of t divided by delta t, right? And what does this become? This just defines the derivative of the displacement function. Right? So what we can see is instantaneous velocity is essentially the derivative of the displacement function. right? So hopefully you guys are tending to notice some patterns here. So whenever terms are defined as the rate of change with respect to another function, we can find the instantaneous change in that function using the derivative of the original function. For concreteness, we saw how velocity was defined as the average velocity was defined as the rate of change of displacement with respect to time, right? And that means that if you wanted to find the instantaneous velocity, and because we know how derivatives are analogous to the instantaneous rate of changes, we can find the derivative of a displacement function with respect to time, and that will give us the instantaneous velocity. Okay? And then just so because a lot of questions relate with speed, distance, displacement, acceleration. Speed is defined as the absolute value of velocity. So if velocity is v of t, so speed is ds over dt, and the absolute value. So you'd still, to find speed, you'd still differentiate displacement with respect to time. But if you get a negative magnitude, you just find the absolute value of that, and they'll give you the speed at the point. And this all comes from the notion of how displacement can be negative, right? Again, if we're at point x and we ended at point x minus h, our displacement is negative h because we're, with respect to x, we're on the left side. Yep. Okay, so now let's go on to acceleration. And here we'll see one of our first applications of higher order derivatives. So acceleration, acceleration is defined as the rate of change of velocity with respect to time. Okay? So again, this whole idea of the rate of change of velocity with respect to time, and the rate, and since acceleration is defined as the rate of change of that, we know that acceleration, so a of t, is just the derivative of velocity with respect to time, right? So if we had the function, a velocity function, right, and we found out the derivative of each instantaneous point at that velocity function, we would be finding the acceleration at every single point, and aggregating all those points together, we would have our own acceleration function. So acceleration is essentially the derivative of velocity with respect to time. But what if we're not given the velocity function? Can we still reach an acceleration, an equation for an acceleration? And the answer is yes, if we're given the displacement function, right? We know that, and so how do we arrive at that? We know that velocity is the derivative of displacement with respect to time. And the derivative of velocity with respect to time gives us acceleration. And if we look at things from the frame of our displacement function, all we're doing is we're taking the derivative of displacement once, and we're doing it again to find acceleration. So acceleration is also equally defined as the second derivative of displacement with respect to time. So depending on what information we're given, we can use these two notions of second derivatives and these equal and analogous definitions to find acceleration and to find velocity, etc. And we don't know how to do this right now, but later on when we learn integration and things like that, we can move the other way. Right now we only know how to move from we only know how to move in one direction. So if we had displacement, we know how to move to velocity, and we know how to move from that to acceleration. But how do we move in the leftward direction, right? We know how to move when we're getting things defined as the rate of change of a certain other term, but we don't know the other way. And the other way we'll find out later when we learn about integration. It's a bit more complex, but still not too difficult. Okay. So a lot of the problems related to acceleration, velocity, and displacement have to do with free fall. And when we're given free fall, we're usually given how displacement is defined, and then from that we find out velocity at specific times and displacement and acceleration at specific times as well. So, yep, that should be it. Maybe if you guys want, and later if I think it's important, I'll cover some examples in relation to motion, and then there's also applications in economics that you can use derivatives for, and I can cover that as well. But hopefully this served as a good introduction.